Hello and welcome to our physical sciences session. My name is Themba Ncube. Today we are focusing our attention on the quantitative aspects of chemical change with a special focus on the mole. The term mole in itself, it talks a lot about, how exactly we quantify amount of matter. How do we know there's a certain amount of matter in a given sample of substance? So we shall talk about the mole quite a lot. Okay, what's the thinking that's going to guide our discussion for today? Okay, without the waste of time, let's look at the thought regarding today's session. Have you ever thought about what is the biggest number you can count? Okay, the moment you start talking about number, it has to do with quantifying. Okay, so what's the furthest that we can count to? So this is the thinking that we want to take off from, so that we guide our discussion in as far as what exactly a mole is all about. Is it about the number? That remains to be seen. Okay, right. So in terms of the quantitative aspects of chemical change, now when we talk about a chemical change, what exactly are we talking about? We're talking about a chemical reaction, substances reacting with each other. Now, when we talk quantitative, we want to know how much. Is it about the numbers? Yes, indeed, it is about the mole. So the mole is actually the quantity that we want to focus our attention on. Now, we'll also talk with respect to the mole in terms of mass, the numbers, in terms of quantities, as well as volume. So that's the focus in as far as today's discussion is concerned. Right. Okay. Now, one big question, how many molecules do you think are present in a glass of water? Right. This is a very, very broad question. Where do we even begin? We know that matter consists of particles. These particles can either be atoms, can be ions, formula units, molecules. So ideally, we would also remember that water consists of molecules. Now, so if we were given a glass full of water, now, the question that we're asking ourselves is, how many molecules of water, can we count inside that sample of a glass of water? So that's the thinking, okay? Right. Now, having said that, okay, we know that particles that make up matter exist in different forms, which is a solid, a liquid, or a gas. So for the purpose of this discussion, we made reference to water as a sample of substance. Okay, so it says all forms of matter consist of small particles. So these particles can either be atoms, molecules, or giant network of atoms, which is actually ionic compounds. Okay, so atoms, they make up what forms of matter? Atoms, they make up elements. Okay, so an element would definitely consist of atoms of the same kind. Now, molecules will be your covalent compounds and elements. Okay, so molecules will be the covalent compounds. Okay, or elements. Okay, remember we have molecules of elements, oxygen, for example, chlorine gas. So molecules are not only for compounds, but it can be compounds or elements, or a giant network of atoms. This is, in terms of the crystal lattice, an example will be ionic compounds, okay, or ionic substances. Right. So these are the particles that actually make up matter, okay, as we know it. Right. Now, so below we have a list of substances, okay? Which of the given chemical formula represent element and which one represents compounds? So the key word is element and compounds. Now, let's go back. In terms of terminology, we know elements are made up of atoms of the same kind, okay? So what you find in the periodic table of elements are actually the elements, which consists, if we are to take into account a specific example of an element, that particular element would consist of atoms of the same kind, okay? But then, on the other hand, if we speak of compounds, what exactly are we referring to? Let's remind ourselves, if we talk of compounds, we're actually referring to those substances, or that, group of substances that actually consist of, different atoms of different elements that are chemically bonded with each other. Different, that is, okay? Now, how they bond, it could either form a formula unit as in, the ionic compound, or it could form molecules. So here we are going to just classify, right? Now, if we look at copper, copper is in the periodic table of elements, okay? So copper is an example of an element. So this consists of atoms of the same kind. Which other one? We can also think about magnesium as an element, okay? But there's something interesting with oxygen, okay? O2, okay? I'll put a block on it just to show that it falls in the same category. Now, if you think of oxygen, oxygen is not a compound. Why? Because these are atoms of the same element that are bonded to each other. It is a molecule of oxygen, okay? However, these atoms are of the same kind. As a result, it represents a molecule of an element. Remember the distinction between a molecule of an element and a molecule of a compound. The difference is that in an element, it's atoms of the same kind, while on the compound, it's atoms of different elements that are chemically bonded or joined together. So this is an element, right? Now, let's look at compounds, okay? Just for distinction, we'll circle the compounds, okay? What's so special about sodium chloride? This consists of two atoms of different kinds that are chemically bonded. So this is a compound, while water is another example of a compound, okay? And again, we can also say carbon dioxide is a compound, while also copper sulfate is another compound. So those that we've put in blocks are actually our elements. So our key is such that this would represent an element, right? While that would represent a compound, chemical formula for compounds, okay? Right, so this is just about the classification, right? Okay, now elements are substances that consist of atoms of the same kind. That's how we arrived at that classification, okay, in the previous slide. And then secondly, atoms of an element all have the same number of protons. Now, if you take, for argument's sake, if we can go back, we can take copper, or let's say magnesium, for argument's sake. If you look at magnesium as an example, okay, magnesium is element number 12, right? It has a mass of 24, okay? Right, so the Mg is the symbol, where 12 represents the atomic number, which is actually the proton number, while the 24 recognizes the nucleon number, which is the sum of the protons and neutrons in the nucleus of that atom. So if we talk of elements, they must have the same number of protons. So the number of protons in all magnesium atoms is actually 12, right? Okay, that's what it simply means. And then atoms of the same element may have different masses. Okay, this brings us to another, dimension to it. Yes, the number of protons is the same, yet the mass will actually differ. The difference arises as a result of the number of neutrons. So these elements that have got the same number of protons but different masses, we call them isotopes. Okay, we call them isotopes, right? So these isotopes, they exist. Let's say we can have element X, all right, with, let's say we would say this is number 17, okay, 35, okay, and then we can have X, okay, which is 17, and then 37. Okay, you'd realize that the number of protons is the same for this element, yet the number of the atomic mass is 35 and 37. So this element X is an isotope. It has got isotopes, right? We'll talk about that at a later stage, okay? So particles of an element can be single atoms. In the example of noble gases, you can have, for argument's sake, helium as an example. Okay, so this consists of atoms that make up this element, or it can be molecules. Now, these molecules, in the case of oxygen, this is a molecule of an element, okay? Hydrogen is a molecule of an element. But what's so special about these two is that these are diatomic, okay? So what do we mean when we say they are diatomic? It means a molecule of each of these elements exists, in pairs. So a unit consists of two atoms of the same kind that are actually joined together. We also have other molecules of an element which is like sulfur, in which a single molecule consists of 8 atoms that are joined together. And then we also have giant or molecular structures or network structures in the case of carbon as well as copper, right? So these are examples of what exactly makes up particles that make up matter, okay? So if we shift our attention to compounds, these are substances that consist of atoms of 2 or more different elements. Remember, the elements in a compound must be different and they must be chemically joined. If they're chemically joined together, sometimes we say that we'll describe them as being bonded to each other, okay? Right, so we'll talk about chemical bonding at a later stage, but these particles in a compound can either be molecules if they are covalent. So for molecule, it has to do with covalent substances where they share electrons so that they become stable, or giant network structures, which in most cases are ionic, right? Okay, and then we can also talk about molecules found in a compound which has got bonding between atoms. Then the word core means share, okay? So the moment you see the word core, it says there is some sort of sharing while the bonding is taking place between the atoms. So water, carbon dioxide, and this hydrocarbon. For now, let's call this a hydrocarbon, okay? Let's call it a hydrocarbon. Why do we refer to it as a hydrocarbon? Because it consists of carbon and hydrogen atoms that are chemically bonded to each other. So these are molecules because they are covalently bonded to each other, right? Okay? Now, in as far as the giant network of atoms for a compound, atoms are bonded by way of ionic bonding. We've already mentioned that. So that's the distinction between the particles that make up, an ionic compound versus those that make up a covalent compound. So if it's ionic, they give us a giant network of atoms or a compound. It could be, if it's an atom, then it means it's an element in the form of an element, right? Then compound, obviously, 2 or more different elements that are chemically joined together. Okay, then when it comes to the chemical formulae, okay, remember, when we represent substances, we use chemical formulae. So chemical formulae comes from, the formula of simple elements that we know from the periodic table. Now, the moment they start to bond with each other to form compounds, be it covalent or ionic, we are able to represent the molecular formula of those compounds using, symbols, right? So an example, this is a combination of sodium and chlorine, which is sodium chloride. This is a combination of potassium and oxygen, which is potassium oxide. Take note, oxide. And then this is copper sulfate, right? So these are just simple examples. Now, the question here is, how many molecules do you think are present in a glass of water? We're talking about molecules. Why are we saying molecules while referring to water? Okay, what's the formula for water? H2O, okay? Why are we saying this is a molecule? This is a covalent compound, right? Let's just break it down so that we understand the question in the right context. So this is a covalent compound. That's why we can refer to it as a molecule. So the question is how many? And you must also remember that our focus is on quantifying, actually getting that number. And remember the first question that we asked to say, how far can you count? What's the furthest you can go? So it has to do with the numbers. Now, given a sample of a glass of water, now we want to determine exactly at the end of this session how many molecules are actually present in that sample. Let's understand that molecules, they can be either molecules of a compound or element. But in the case of water, when we talk about a molecule, we're talking about a molecule of a compound, okay? Now, the number that we're interested in is how many molecules can we count inside, that sample of water, which is, a glass full, okay? So that's the basic idea, right? And then the question is, how many molecules do you think are present in a glass of water? So the thinking is, water, first of all, is a compound, YH2O, okay? That's our starting point. So that's the molecular formula, okay? Made up of molecules, okay? We need a method to count the molecules. We could find the mass. So now we are quantifying how heavy is, how much matter. So this is amount of matter, okay? Remember, matter is anything that has got mass and can occupy space. So mass is amount of matter, okay? So I'll put that in brackets, okay, amount, right? And we use that to calculate the actual number of molecules, right? So we will also like to focus our attention on exactly what a mole is all about. But having said that, let's just hold the thought about the number of molecules present in a glass of water as a sample, or just to, to give us something to think about in terms of quantity, okay? Then from there, after the short break, we'll try and look at the mole, which is the bigger concept. Let's take a short break for now.